Okay, so in the last video I talked about Grassmannian over finite fields. Now I will talk about Grassmannian over. So let's start with Grassmannian over reals. So suppose I look at this object GR2 R3. So these are all two-dimensional subspace of the three-dimensional vector space of the real number. So then you have this 3 by 3 invertible matrices over real number GL3R. So this is the Lie group. This is a nice Lie group. So why this is a Lie group? Because GL3R can be thought of as open subset of R to the power 9, right? So this is a open subset. This is an open subset of, can be thought of as an open subset of R to the power n, where R to the power n is equal to standard Euclidean topology. So GL3R is open subset of that. So open subset of a manifold is always a manifold, and this is a group, and you can show that under this standard manifold structure, the group operation is also smooth. So that's what makes GL3R into a nice Lie. And this Lie group is acting on GR23. So which is just set of all two-dimensional subspace of R3. And this action is transitive. And the logic is same. The logic is exactly same as it was for the logic in case of finite. This is true for any vector space. If you have two different two-dimensional subspace, you can find a linear transformation which maps one to the other, and vice versa. Any linear transformation, any invertible linear transformation will map two-dimensional subspace to another two-dimensional subspace. The space GL3R acts on this space GR23 transitively, and yeah, and then you can look at the stabilizer. So how to write down the stabilizer? How to write down the stabilizer? So I already explained this in the last video, that you can choose a basis for that two-dimensional subspace and then extend that basis to the whole space, and with respect to that basis write down the invertible linear transformation in a matrix form. So then matrix will look like this. So you will have a 2 cross 2 block here, you will have a 2 cross 2 block here, and then you will have a 1 cross 1 block here, and then you will have yeah, 4 entries here. 4 entry, no, sorry, only 2 entries. 3 by 3 matrix. So you have 2 entries here. And of course, now the stabilizer is infinite. The order of the stabilizer is infinite. But this is how the stabilizer looks like. If you fix a particular point x in the space GR23, that is x is a particular two-dimensional subspace, then the stabilizer of x will be in this form. Yeah. So you have one invertible 2 by 2 matrix here, and then you have another 1 by 1 invertible matrix there, and then you can freely choose these two entries, and you have 0 down there. So this is the way it looks. So now, yeah, now you can easily show that this stabilizer stabilizer of X is a closed subgroup. By closed subgroup, what do I mean? It's topologically closed. You can easily show that GL3R is a nice topological group, and this is a closed subgroup. Whenever you have a Lie group and you have a closed subgroup, then you can define the quotient. So we have this Lie group GL3R, and you have this subgroup stabilizer of X. There is a closed subgroup. So now GL3R modulo the stabilizer of X. That is the space of all left cosets of the subgroups stabilizer X. Right? I think. Okay, so let me just write down in the general form. So if G is a Lie group, and H is a closed subgroup, then G mod H is also. What is G mod H? I mean, this H, the subgroup H is not necessarily normal. So when I write G mod H, I mean space of all left cosets of H. That is also a that is a smooth manifold. Not also. That is also a smooth. Yeah, that is a smooth manifold. So this object, this GL3R modulo, a closed subgroup. This is what is called a homogeneous space. So whenever a Lie group, uh, G is acting on some manifold in a transitive way, then that space is known as a homogeneous space for the Lie. And any homogeneous space is isomorphic to that Lie group modulo some closed subgroup, where the closed subgroup is precisely the stabilizer of a particular point in that manifold on which the group is acting. And what is the dimension of the manifold? The dimension of the manifold G mod H is just dimension of G minus dimension of H. That is a basic thing. So just look at this matrix form carefully. Then you will see what is the dimension of the stabilizer. So first of all, what is the dimension of GL3R? GL3R dimension is 9. It's a 9-dimensional object because we have 9 entries and you can choose them from open subset in R9. It is a 9-dimensional object. And what is the dimension of this stabilizer? So you have this 2x2 block. So you have 4 entries, and then you have 1x1 block. So you have 1 entry, and then you can freely choose these 2 entries. So 4 plus 1 plus 2. So overall, this is how much? 7. So this is a 9-dimensional object, and the dimension of the stabilizer is 7. So what is the dimension of the homogeneous space? This homogeneous space, dimension of this as manifold. By dimension, I do not mean the dimension of the vector space. This is not a vector space. This collection is not at all a vector space. The collection of all two-dimensional vector space of R3, this is not at all a vector space. This is a manifold. This is a smooth manifold. What is the smooth manifold? that is a quotient of a Lie group. Quotient of the Lie group GL3R. And what is the dimension? So this is the dimension is 9 minus 7. So basically 2. So these are two-dimensional smooth manifold. So in general, you can show that. In general, you can show that dimension of GRK Rn that is just k into n minus k. I'm leaving this as an exercise. Just follow the exact argument that I have already used. The calculation of GR2 R3. Same argument will go through, and you will see the dimension of this Grassmannian. By dimension, I mean the dimension as a smooth manifold. This is just k into n minus k, and this is an important object because it's a quotient of a Lie group. Quotient of a Lie group by a closed subgroup that is a homogeneous space. That's why these objects are important. And so this is the point of view of manifolds. So this can be viewed as a smooth manifold, which is also a homogeneous. So let me just repeat what I have said. This is the basic fundamental theorem that I am talking about. That is, G is a Lie group. If you do not know what a Lie group is, let me just repeat the definition. This is just a group which is also a manifold and a smooth manifold, and the group operation are smooth with respect to the given manifold structure. So you take a Lie group G, you take a closed subgroup, then the quotient G mod H. H is not necessarily normal, it's just a subgroup. By G mod H, I mean the space of all left quotients. That space inherits a smooth manifold structure. That is a smooth manifold of dimension G minus dimension H. So this GL3R acts transitively on GR2R3, and GR2R3 can be identified with nothing but GL3R modulo stabilizer of X, where X is a particular two-dimensional subspace. And then you have seen that the dimension of the stabilizer is just 7-dimensional by this argument, and GL3R is a 9-dimensional object. The dimension of the Grassmannian 2, R3 is just 2-dimensional, and in general you can prove that dimension of GRK Rn is k into n minus k. You can also do this exercise and write down the solution in the comment section. And the last thing I want to talk about, that is okay, there are many things. Maybe in future, in future, uh, I might talk about cohomology of Grassmannians. You do not know what is a cohomology, I will just explain everything from the scratch. So cohomology of Grassmannians, and this is um, this is this is a very interesting object where many things are interconnected with each other. This is, say, like geometry, combinatorics. By geometry, I mean mostly algebraic geometry. Algebraic geometry, combinatorics, presentation theory. So all these things are, I mean, the cohomology is of Grassmannians is a platform where all these three things are all these three things interplay with each other. Geometry, combinatorics, representation theory, and many other things. So this is really a cool and interesting object. In future, I will talk about cohomology, but now I want to finish by describing Grassmannian as an algebraic variety. How can we do that? That is also very easy. We change the color, yeah. So first observe one thing. Suppose you have a vector space, let's say R3. Okay, and then I can define a projection operator. Projection operator uh, P from R3 to R3. By projection, what I mean, first of all, this is a idempotent, that is P square is equal to P, and then rank of P is, let's say, I'm interested in the two-dimensional subspace, space of all two-dimensional subspace of R3. I'm interested in that Grassmannian, that is, I'm interested in the Grassmannian GR2 R3. So I'll be looking at projection operator from R3 to R3. So what are those things? Those are just idempotents, P square equal to P, rank of P equal to 2, and then the image of P will be that two-dimensional subspace. I'm just giving a very rough idea. I mean, you can work it out on your own. I'm just giving some rough idea. I'm not being very rigorous here. I'm just giving you the idea. You can figure it out. Look at all possible invertible matrices P, so that P square equal to P, rank P equal to 2, and the image of that linear transformation P will give you a two-dimensional subspace. So the GR23 can be described by all such matrices. And yeah, and if you observe that this P square equal to P, this that this rank of P is equal to 2. These are all, I mean, polynomial conditions. So all of them can be described polynomial using polynomial equation. So that will basically that is how you can define some algebraic variety structure on the space GR2 R3. That is just some rough idea, not being very rigorous. So yeah, I think that's all I wanted to talk about. So let me just conclude by summarizing what I've said. Like if you're on the combinatoric side, then you'd be interested in counting cardinality of the set, which is itself a very interesting problem. And if you are a geometer or you're a geometer or a topologist, then you'd be interested in objects like GRK, RN. In fact, these are nice projective varieties. And then things like GRKCN, these are nice uh, compact objects. These are these are nice uh, compact complex manifolds. So, so yeah, I mean these are very well-known and interesting objects which can be studied. And yeah, maybe in future I will explain the cohomology and then explain how the cohomology of the Grassmannian is important in combinatorics also. So yeah, that's it for now.